Okay, we're going to talk about how joints and long bones can act as levers. And there is a part in this where you're probably going to feel a little overwhelmed, and I want you to just stick with me and promise me you'll read through the section in the book, or maybe watch this video a couple times because it does get a little technical, but it's really not too bad if you just take the animations for what they're worth. So, long bones are acting as levers to enhance the speed or power of the limb movements. And so let's make sure we understand what a lever is from physical science. Simple machines. A lever is any long, rigid object that rotates around a fixed point called a fulcrum. And we're going to see where the fulcrum is going to depend on the types of our levers, but the rotation occurs when an effort applied overcomes the resistance at some other point. So if you take a look at this lever, we can see our fulcrum and we see our effort is at one end. That end between the effort and the fulcrum is called the effort arm. And then the other side is where the resistance is, or the load, and that side is called the resistance arm. So we can have an advantage from a lever. It can be into two different kinds of advantage. We can have more force against the resisting object than the force applied to the lever. So an example like that would be a human moving a very heavy object with the help of a crowbar. Or the advantage could be to move the resisting object farther or faster than the effort arm is moved. So this is an example like the movement of rowing a boat. But one lever cannot have both of these advantages. So as one increases, the other decreases. So we're going to use the phrase mechanical advantage, or MA, of a lever. That's the ratio of the output force to its input force. So we're going to calculate the length of the effort arm divided by the length of the resistance arm. Again, I know this feels really overwhelming, but just kind of stick with me. This is just showing you how different joints, in my opinion, how they are making either really large movements or really small movements. So the mechanical advantage, again, is the length of the effort arm divided by the resistance arm. And remember, this is all dependent on where the fulcrum is, where the effort is, where the resistance is. And so if that mechanical advantage is greater than 1, the lever is producing more force than the force exerted on it. Or if the mechanical advantage is less than 1, the lever produces more speed or distance, but less force than the input. So here's the example of the contraction of the biceps brachii muscle puts more power into the lever than we get out of it, but the hand moves faster and further. So the mechanical advantage would be considered less than 1. So let's look at 3 different types of levers. First class lever. If this type of lever has the fulcrum in the middle, right in between the effort and the resistance, and so here the mechanical advantage is equal to 1. We see this in the muscles of the back of the neck and the weight of the face. And here's an animation of what that looks like. So that's first class. A second class lever is where we see the resistance is between the fulcrum and the effort. And here our mechanical advantage is going to be greater than 1. So an example would be resistance from the muscle tone of the temporalis muscle, which is between the jaw joint, and the pull of the muscle on the chin as it opens the mouth quickly. Now, I think it's really hard to go from a picture of a board and a picture of a wheelbarrow to a picture of the body part, but I love how these are all labeled, and so it does help kind of make that segue. And here's a picture of what that type of lever is looking like. And then the third class is where the effort is between the resistance and the fulcrum, and these are the most joints that we see in our body. And the picture or the animation of that one looks like this. So most of our joints are this third class type of lever. We'll also need to talk about range of motion when we get into our different types of synovial joints. It's the number of degrees through which a joint can move. It is an aspect that we compare for joint performance, and it is a physical assessment of a patient's flexibility of their joints. So this range of motion is determined by a few factors: the structure of the articular surfaces, the strength and tautness of the ligaments and the joint capsules, and then the action of the muscles and tendons. So all three of those play into the range of motion. A moving bone has a relatively stationary axis of rotation. It passes through the bone in a direction perpendicular to the plane of movement. We do have one multiaxial joint, that's the shoulder joint. It has 3 degrees of freedom, or 3 axes of rotation. Our other joints that we see are either monoaxial or biaxial. So we're going to look at classes of synovial joints. So this is within the category of synovial. We're going to label the 6 different classes and be able to identify the shape and give an example in the body. So ball and socket joints are smooth hemispherical heads that fit within a cup-like socket. I think these are the easiest. The name says exactly what it looks like. The examples are your shoulder or your hip. And these are the only multi-axial joints in the body, are these ball and socket joints. They have the largest range of motion, 3 axes of rotation. Okay, then we have condyloid joints. They have an oval convex surface of one bone that fits in the complementary shaped depression of the other. So we see this in our wrist and at the bases of our fingers. These joints are biaxial. They have a movement in 2 planes, and we're going to identify all these names of movements. Saddle joints are where both bones have an articular surface that looks like shaped like a saddle, concave in one direction and convex in the other. We see this at the base of our thumb and where the clavicle meets with the sternum. These are also biaxial joints. They're more movable than condyloid or hinge joints, especially at the opposable thumb. So plane joints are flat surfaces where the bones slide over each other and is relatively limited movement. It is usually a biaxial joint. The carpals of the wrist, the tarsals of the ankle, and then in between the vertebrae. Even though any one joint moves slightly, when we have multiple joints, like in the wrist and the ankle and the vertebral column, then we see considerable movement. So it's kind of weird to say that they have limited movement, but then to say biaxial. But when you have multiple joints in one small area, then we have a larger movement. Hinge joints have one bone with a convex surface that fits into a concave depression of the other bone. We see this at the elbow and the knee and fingers and toes. And they are monoaxial. They only have one plane or one axis of rotation. A pivot joint is the bone that has a projection that's held in place like a ring-like ligament by a ring-like ligament, and the bone spins on its longitudinal axis. So we see this in our joint between the axis and the atlas, and we see this in the radial-ulnar joint that allows the radius to rotate. We will talk about pronation and supination in the next video. These are monoaxial joints. So the movement of synovial joints, we're going to go into all the movement names, but the vocabulary of the movement, these are kind of in pairs. So the movements are going to be presented in pairs with opposite or contrasting meanings. It is important to understand the anatomical planes and directional terms to help with these names. Zero position refers to the position of a joint when a person is in that standard anatomical position. I'm assuming that you've done this in the lab, but just in case you haven't, that's with standing and your thumbs are pointing laterally, so they're pointing out. So that is important to kind of think about as zero position. So joint movement is described as deviating from that zero position or returning to it. And we're going to save this list of movements for the next video.